Hey everybody, this is Chris McClure again. Wanted to hit the material in section R3 with you today. Today is Tuesday, May 28th, 2013, and I just came back from a long trip to South Carolina. I'm back at the Ankeny campus and ready to make some forward progress in the course. All right, so you can expect that most days of the week, Monday through Friday, that I'll be recording lectures for you to be looking at and working on the homework. Now, there are some people who have not yet registered with My Math Lab, and I want to make sure that everyone gets on My Math Lab as soon as possible, but there's like 4 people who still haven't. And I will be sending those people an email to basically ask them what the holdup is and what can I do to help them get registered. All right, so let's go ahead and take a look at this material. It's not really earth-shattering. It'll be a good review for you. Okay, so let's go take a look here. Pull out my magic pen here. Let's see, what color will we go with today? All right, well, dark blue is always good. All right, so we are going to now take a look at one of the important ideas that resonate throughout all of mathematics, and it's just a simple idea from geometry that talks about the relationship between the lengths of the sides of a right triangle. And here it is. We've got a right triangle. How do we know it's a right triangle? Well, we're not always going to be told that this angle is a 90-degree angle. Every right triangle has a 90-degree angle. But we will usually see this little notch, this little square right there in the corner, indicating that that angle is 90 degrees, and therefore the triangle is a right triangle. The 2 legs adjacent to the 90-degree angle are called legs, and then the side of the triangle that is opposite the 90-degree angle is called the hypotenuse. And the Pythagorean theorem basically says that the square of the one leg plus the square of the other leg, lengthwise I should say, is equal to the square of the hypotenuse. And that relationship holds for all right triangles. So here's a real quick example. So suppose that we've got a right triangle. One leg is the length of 4. All right, so here's our length of leg 4. And the other leg is length 3, and then what is the length of the hypotenuse? Well, we can use the Pythagorean theorem that says that the square of the hypotenuse is equal to 4 squared plus 3 squared, which is 25, and that must mean that the length of the hypotenuse is 5, because 5 squared is 25. Okay? All right, sound good, everybody? Moving along here. And also we can go in the reverse of the statement of the Pythagorean theorem. Now, if you were to go back to this statement here of the Pythagorean theorem, it says if we have a right triangle, then here's the relationship between the 3 sides. Now, we could also take the converse of it, and it turns out to be true. That basically says is if that relationship exists between the 3 sides of a triangle, then that must mean that the triangle is a right triangle. Okay, that's basically what it says. So, if you happen to have a triangle whose sides are of length 5, 12, and 13, for example, so if you've got this triangle here, you have one leg of length 5, another leg of length 12, and the well, and the other side is 13. And then notice that, 5 squared plus 12 squared is equal to 13 squared. Well, because that Pythagorean relationship exists, that must mean that the triangle really is a right triangle. Okay? So, and the hypotenuse, of course, is the longest of the three sides opposite the right angle. Okay? Moving along here. So here's an interesting application of the Pythagorean theorem. So imagine that you're standing on top of a tall building. Now, provided that you can look out on a clear day with binoculars or a telescope, how far out on the horizon can you see? And here, I'll show you how this goes. Now, suppose that the height of this building is 1,437 feet in this example. How far out can you see? So here's kind of a picture of what this looks like if you were to look at the Earth. All right? Here's the center of the Earth. Now, the radius of the Earth is approximately 3,960 miles. Then the radius plus the height of the building will be how much? Well, you can express either in feet or in miles. If you were to take that, height. Now, let's just go ahead and round that to 1,450 feet for the height of the building. And then, so 1,450 over 5,280 will be the number of miles. And you add that to the radius of the Earth, and then you look at this picture right here. We've got a 90-degree angle, a 90-degree triangle, I should say, where this short leg here is going to be the line of sight from you at the top of the building. And that point on the Earth's surface, where past which you can't see anymore. And then the other leg, of course, is that radial line segment from that point where your vision stops on the surface all the way down to the center of the Earth. And then the hypotenuse is that line segment from the top of the building down to the center of the Earth. This is a right triangle. Now, because of the fact that this is a right triangle, then the Pythagorean theorem holds. Now, we need to solve for this distance d, which is the distance from the top of the building down to the surface of the Earth, past which you can no longer see. Let's call it d. Let's solve for d. Now, we know from the Pythagorean theorem that says that d squared plus the radius, which is 3,960 miles squared, is equal to this hypotenuse, which is this right here, squared. Remember, the 3,960 plus 1,450 over 5,280 miles is the total distance from the top of the building down to the center of the Earth. So we have this relationship. So that means that d has to be in miles when we solve for d, because this is in miles and this is in miles. Okay? Now, we have this equation, solve for d. Basically, subtract the 3,960 squared from both sides, and then take square roots of both sides. Okay? So that's what we're doing here. And then take the square root of the result of this squared minus this squared. So take the square root of this, and you get approximately 46.64 miles. As in, from the top of the building, you can see about 46.64 miles. on a very clear day. Okay? Alright, let's just review all the geometry formulas that you probably already know and love. For a rectangle, we know that the area is going to be the length times the width. Alright, the length times the width. The perimeter, that's the distance around the outside, so that's going to be twice the width, right? Plus twice the length. So length plus width plus length times width. That's twice the length plus twice the width. That's the perimeter. The area of any triangle is going to be 1/2 times the base times the height. The height is taken from the highest point on the triangle when you drop a perpendicular down to the base, where the base we typically take to be the longest side of the triangle. We don't always have to do that way. You know, like for example, if you have an isosceles triangle where you have two sides the same, then we could take this side, which is not the side that's equal to the other two. We could take this as the base, for example. And the highest point is taken relative to the base. Then we have our favorite shape of all, the circle. Remember, pi is that irrational number where you have the circumference divided by the diameter. So that means that the circumference is equal to pi times the diameter, but the diameter is twice the radius. So you could write the circumference is 2 times pi times the radius. Also, the area of a circle is pi times the radius squared. Another important formula. If you have a rectangular box where each of the 6 sides is a regular rectangle, then the volume is going to be the length. Hi there. Length times the width times the height.
Ditto master.
Wow, that's always cool.
Sorry.
And the surface area, sorry about that. A colleague came in to show me something that I haven't seen for many years. Oh, and going back to the rectangular box, says that the surface area is going to be the sum of the areas of the 6 rectangular faces. So, for example, you see the 2 times the length times the width. Well, the length times the width will be the area of both the bottom of this box as well as the top. And twice the length times height. Well, that would be the front and the back, those two together. And then 2 times the width times the height. The width times the height would give you the area of either end. So you multiply by 2 and you get the 2 areas. So you add them all up to get the total surface area. Now, the sphere, my favorite 3-dimensional object, it has a volume of 4/3 times pi times r cubed, where r is the radius. Surface area, 4 times pi times radius squared. All right. I will be able to prove these two once we get into Calculus 1 and then Calculus 2. Okay? Certainly in Calculus 2, you will come away knowing exactly where these formulas come from for the volume and for the sphere. Probably, actually, when we get to Calc 3, it'll be actually even easier for us to use multidimensional calculus to calculate those two quantities. Anyway, regardless. Now, for a right circular cylinder, now what we mean by a cylinder is basically where you have a circle projected in the 3rd dimension. in a linear fashion, like you see here. Volume is pi times the radius squared, which is the area of the circle on the top or the bottom, and then times the height. That'll give you the total volume. Now, the surface area of the right circular cylinder, well, that's going to be the sum of the areas for the top and the bottom and the lateral area. Now, pi times r, 2 times pi times r squared will give you the area of both the top and the bottom together. Pi r squared, of course, is the area of the circle. Multiply by 2, that'll give you the top and the bottom. Now, for the 2 times pi times r times h, now think about this lateral area. Imagine if you were to take the side of this can after you punched out the top and the bottom, and you were to snip down the length of this and roll it out, flatten it out. What would you have? You would just have a big long rectangle. And the length of this rectangle is 2 times pi times r, and the height is h. So 2 pi r h will be the area of the lateral surface. So plus the area of the top and the bottom will give you the surface area of the right circular cylinder. Okay? All right, so here's a quick example here. Suppose that we've got this shape right here, kind of looks like an ice cream cone. They're calling it a Christmas tree ornament. How do you find the area of it? Well, here you've got this top piece right here. That's half a circle. Radius 2, which is half the 4. So 1/2 times pi times the radius squared, which is 2. So we have 2 squared. And then we have this green triangle. Now, the base is 4, and the height is 6. So the area of that green triangle is 12. And the area of this semicircle will be 2 pi. So 12 plus 2 pi will be the total area. All right? So 12 plus 2 pi. And on your calculator, let's put that into our calculator. 12 plus 2 pi, about 18.28 square inches, or centimeters. 18.28 square centimeters. Okay. Moving along here. Now, one of the most useful ideas from geometry of triangles that is used to prove many other things, and especially in higher level math, but also in trigonometry and stuff, is the ideal of similar triangles. But we also have congruent triangles, which basically mean triangles that are really the same. A similar triangle is similar to congruent triangles in that, they look a lot alike, except congruent triangles are exactly the same. Similar triangles mean that they look to have the same shape, but they're a different size, potentially. Now here we have 2 congruent triangles where the lengths are the same and the interior angles are exactly the same. This 100 degrees is the same as this 100 degrees. This 50 is the same as this 50, and this 30 is the same as this 30. And this side is equal to this side. The B is equal to E. The A is equal to D. C is equal to F. Those two are the same. Now, you might not have all 3 angles and all 3 sides, but as long as you have 2 angles in the side or 3 sides, then you should be able to determine that the two are triangles are congruent. So if you have angle side angle, for example, meaning if for the two triangles you have an angle and another angle and the length of the side in between. Now, using trigonometry, which we'll hit next semester, we could always find the other two sides and the third angle. But we don't even need to do that as long as we have angle side angle for the one and angle side angle for the other and verify that they're the same, then the two triangles are congruent. Or if you have your two triangles and the three sides are the same, that means that the interior angles are the same as well. And so, provided that the three sides are the same for the two triangles, then the two triangles are congruent. If you have side angle side for the two triangles as being the same, the two triangles are congruent. Congruency means is that the two triangles are exactly the same size. The ratios amongst the sides are the same. The interior angles are the same, and so forth. Now I can honestly say we use congruency once in a while, but we use similarity of triangles a lot more often to make geometrical arguments. Now, two triangles are similar if the corresponding angles are equal and the lengths of the corresponding sides are proportional. Now, here's an example of two triangles that are similar. The two angles, the interior angles for the two triangles are the same. Here you've got 80 degrees, 80 degrees, 70, 70, 30, 30. As long as the interior angles are the same, then you have two similar triangles. So we could say that, for example, B is to E as A is to D. So let me say that in terms of an equation, or what we call a proportion. B is to E. So B is to E as A is to D. For example. Or we could say that C is to F as, I don't know, B is to E. Or even the ratio could be written like this. F is to D as C is to A. Okay? The proportions hold between the two triangles. Now, how do you determine that two triangles are similar? Well, you could look for an angle-angle case. If you have two adjacent angles being the same between the two triangles, then the two triangles are similar. Side by side, meaning, look, the two triangles have sides that are proportional to each other. So you look at this bigger triangle and the smaller triangle. Now notice that for the smaller triangle, the length of the longest side is 10, and then look up here to the upper left that this side is a 5, which is half of the length of the longest side, which is 10. That same relationship holds for the big triangle, 30 versus 15, for example. Or you could look at the smaller triangle, 10 is to 6, as 30 is to 18. Or you can go 5 is to 15, going across the two triangles. So 5 is to 15, as 10 is to 30. That relationship holds as well. That proportion is true. Or maybe 18 is to 6, as 30 is to 10. All right, so And there's what, 6 different proportions that you could write that are all true. Or if you've got side angle side that holds for the 2 triangles, where the 2 sides are proportional to each other, meaning you could write, 12 is to 4, for example, is the same as 18 is to 6, for example. Or you could write, 12 is to 18 as 4 is to 6, for example. So if the sides are proportional across the 2 triangles and the interior angle in between is the same, then the 2 triangles are similar. And what can you do with similar triangles? Well, here's an example here. Well, here we're told that these 2 triangles are similar, so we know that the interior angles are the same. 30, 60, 90. This is for the smaller triangle. Now, for the larger triangle, we see that this side is length 5. For the smaller triangle, that length is 3. Now, for the longer side, for the smaller triangle, that's 6. For the larger triangle, that's x. So to find x, we could say, as one example of a proportion that you can use, is that x is to 6 as 5 is to 3. And then, of course, you could solve for x. Multiply both sides of this equation by 6, so you've got x is equal to 10. For example. Or you could say 3 is to 5 as 6 is to x, which is essentially the same, except both sides are reciprocal to what we already talked about. Okay, so solve for x. See, the hard part, folks, is setting up the equation. Once you set up the equation, then you could solve for the variable, no problem. Now, if you've ever wondered where the equation in the Pythagorean formula comes from, where if you have a right triangle where you have A, B, and C, where A and B are the 2 legs and C is hypotenuse, and C squared is equal to A squared plus B squared, then here's one way of proving this equation holds. Now look at this picture right here. Beautiful, right? You got this big blue square. The length of each side is A plus B. A plus B, A plus B, A plus B. And you've got this interior square off at an angle where the corners of this interior square are at the point where the side is divided into a length A and length B sub-lengths. Now, you could set up an equation that says is that if you look at the individual 5 pieces within the large square, like this piece right here, this one, and this one. Now, each of those blue triangles has an area of 1/2 times AB. And if you multiply by 4, then you've got 2 times A times B as the sum of those 4 blue triangles. And then the pink square has area of C squared. Okay? So the sum of the areas within the big blue square should be 2AB plus C squared. But the length of each side of the big square is a plus b. So a plus b squared is equal to 2ab plus c squared. So after a couple of steps of algebra, then we get the c squared is equal to a squared plus b squared. All right, the details are in the textbook on page 35. I'll let you take a look at it, but it's not like someone just dreamt it up someday. They were able to mathematically prove it. And right now there's, I don't know, 30 or 40 or 50 different proofs out there, but this was one of the early ones and favorite ones that people like to discuss in proving the Pythagorean theorem. All right. We could also prove the converse of it, that basically says, and I think I already mentioned it at the beginning of this recording, is that if you know that the relationship between the three sides of your triangle is given by this equation, then you know that, therefore, the implication is that the triangle is a right triangle. So it's an if and only if sort of proposition that a triangle is a right triangle if and only if the equation holds. All right, so that's it for section R3. Tomorrow I will record a lecture for section R4 where we'll get into playing around with polynomials, okay? So take care, and I've already posted some new homework for you to start looking at. If you haven't gotten signed up with my math lab yet, you'll be getting an email from me real soon. All right, take care, goodbye, and I'll see you tomorrow.